Swayam Prabha. Digital India. Educated India.
Yeah, good morning, everyone. So we are in the second day of the Gyan course on advanced manufacturing techniques and process monitoring. So hope you had yesterday a lot of informative sessions. So I have given an overview about the advances in manufacturing techniques, and Professor Shreyas Melkote was talking about the surface engineering and then various applications, water jet peening, and also he has talked about some of the even laser peening aspects, and also your visit to the lab I think would have given you an insight into how practically the setup or and the equipment is. So today I'm going to talk about femtosecond laser micromachining and their applications. As yesterday, Professor Shreyas Melkote was trying to define what is the lasers. So laser is nothing but light amplification by stimulated emission of radiation. It is actually probably in your high school you might have studied that. So you have a lasing media here, and then we are going to pump the light into it. On one side we have totally reflective mirror, on the other side we have a partially reflective mirror. So once the light here reciprocates between these two mirrors, once the energy exceeds above the preset limit, so the laser beam comes out from here, and it is a monochromatic light, and it is a very low divergent, and it has a good coherence, and that is the reason lasers have a lot of advantages. So where they can travel a long distance, and also we can have the power of the laser. So even the pointer, so what we use during the presentation, so that is also laser, and you can have even the lasers, so wherein so you can heat up even the celestial bodies. So that much is the power which can vary. So actually, in my childhood, I was always fascinated about these lasers, and then we used to play with the laser pointer, and then we used to talk. But I'm glad that now I'm able to work in this area, and we see a lot of interesting aspects in the lasers and the laser micromachining. And when we look into history, so it is really interesting. So where the phenomena of the laser production was predicted even long before the lasers were actually invented. So right from Max Planck to Einstein, so then John E. Emmett. So all these people have actually told that there is something which is possible for the emission. So then later we see that Townes and other people, so they have worked, and finally it became possible that lasers were invented. And initially, actually, when lasers were invented, they thought that okay, it's a very interesting phenomena where you can emit the radiation, but we don't think there is any application. So that's what they thought. But now, after a few decades, we find that the laser applications in every field of engineering, you take any field of engineering and even sciences, so every field has the application of lasers. So as I said, right from the pointer, even to the eye surgery, medical field or engineering field, or even for measurements, everywhere the lasers are being used. So then there were development of lasers from continuous lasers. So they switched to pulse lasers, and the inventions went on till we are here now. So where we are able to produce not only the continuous lasers, but very short pulse, ultra short pulse lasers, and with the powers which are ranging from low to very high. And also based on the lasing media, what we are using, so we can actually classify these lasers into gas lasers, liquid state lasers, solid state lasers, semiconductor lasers, so free electron lasers. So the technologies have been moving on from one mechanism to the other one, so where we are able to produce these type of lasers. Even as yesterday I have mentioned about these types of lasers, so where we have continuous lasers and then we have pulsed lasers. So depending upon in what time we'll be able to produce those pulses. I'm also going to tell you how they are producing actually these very short pulse lasers. And also there are different wavelengths. So we can have the lasers in the visible range, like about 400 to 700 nanometers, or we can also have in the range like ultraviolet or yeah, even infrared. So we can have all these ranges. But generally, what happens is if they are in the invisible range, when the laser is fired, even we will not be able to see. Sometimes it might be even harmful. If you directly look into those lasers, depending on the power, they may cause harm to the eye. And also, if it touches the human skin, they will damage. So thus, if it is in the invisible range, generally they will have a coaxial visible laser. So thus, when you on the invisible laser, there will also be a red color or depending on whatever the wavelength. So we can see a beam, so that we know that there is lasers. And also it can be used as a pointer. So if you want to machine at a particular point, invisible lasers you can't see, so have a laser pointer, laser light, so that you can know where the laser is falling. So thus both the ranges are possible. And the wavelength actually has a lot of influence on what we are going to talk about, what is called as laser matter interaction. So the shorter the wavelength, so they can penetrate, and yeah, so the distance what they can travel, it varies. So thus whenever you want to produce a laser for a specific purpose, so we need to decide what is the wavelength that is suitable. And as I've been telling about the short pulses, which are a very interesting area. So, wherein we have short pulses and ultra short pulses. So, what is this ultra short pulse is? So, it takes 1 picosecond to convert laser energy into heat. Okay. So now if you have a thickness of 1 nanometer layer, so the diffusion actually takes place in 1 picosecond. It can go about 10 nanometers. So now if you can produce these pulses below that, so there what happens is there'll be no time for the heat actually to penetrate into the material, and thus they have a lot of effects, so which I'm going to show you. And before that, we try to define what is that ultra short pulse laser. So now as you see this video, okay, so here the light what it is traveling is the real time. So if the light want to go once, that is the period of the time which is required. And now if the light has to travel from Earth to Moon, so this is the time cycle. Now, when the light is traveling at such kind of an high velocity, the time which is required by light to cross the hair. Okay, if you take a hair and keep it in the path of the light, and the time which is required for it to travel, so that is nothing but a femtosecond. So they say that the time required to travel our hair diameter 60 to 100 micrometers is about 200 femtoseconds. So that is the way how short it is. Now you may ask, why the ultra short pulse lasers are more powerful when compared to the continuous lasers. So usually when you look at the continuous laser, so they say that it's 1 kilowatt, 2 kilowatt, like that, the energy. So now, what is more important here in ultra short or the pulsed lasers is that the instantaneous power. So because it's at the particular fraction of the second when you put the pulse, that will be equal to laser energy, or we can also call it as the pulse energy divided by time, divided by time. So now pulse energy, we can take an example like we have 40 femtoseconds, so 40 microjoules. So if you have that energy, so we can put it in the denominator, 10 to the power of minus 6. Okay, then divided by time. So if you say that the pulse width is 200 femtoseconds, so you put 200 into 10 to the power of minus 15. So now take this minus 15 from denominator to numerator, then it becomes plus, and then 6 zeros if you remove it. So the resultant will be, it's something like 10 to the power of 9. So 10 to the power of 9 is nothing but like gigawatts. So in that short period of time, so you get a huge power. So generally, when we have power plants, so they specify, okay, this hydroelectric power plant is producing this many 100 megawatts, or nowadays it is like a gigawatt, so more power. So that kind of an high power, instantaneous power it's going to produce in that short pulse, and with that orders of energy, so we can actually evaporate any material. So that is actually basically called as the laser ablation. So yesterday, I think I have mentioned that term laser ablation, but we have not told you how exactly it happens. So now you can look here. So we have the material. So then put the laser beam. So then what happens is generally, if it is a continuous laser, so there will be heating which will be taking place, and a small amount of surface melting which will be taking place, and then surface starts vaporizing. Then there will be a flume of plasma which will be formed, and then when it exceeds a particular pressure, so it actually ablates or it explodes, and there it will be removing the molten pool of material when it has exploded. So that is what actually will be happening. Now when you look here, if it is a ultra short pulse laser, almost we go from this stage to the step E. So you put the pulse, and then immediately we see that the laser ablation takes place and the material is removed. So thus the ablation happens in the 5 steps, but in ultra short pulse laser, so we see that it happens like in 2 steps, where immediately it is exploded. So but actually when we look at the short pulse lasers or continuous lasers, so we'll see that there'll be an area which has been affected by heat. So when we have the shock wave travels, then we have a melt pool zone, and then the heat affected area, high heat affected area, and then lower heat affected zone. And also we find that some of the molten metal which has been exploded, and then it splashes, and sometimes it adheres to the surface itself, and that is called as the recast layer. So then recast layer is melted, and then it will not have the same strength as the parent material. So thus we don't want that layer to be there. But actually, if you look at short and ultra short pulse lasers, so the heat affected zone, it significantly reduces, and if you go down even to the shorter period, 10 to the power of minus 18 or minus 21, It's also possible these days. So there, the heat affected zone almost tends to zero. But still, sometimes when we have machine on our laser, if you don't give the correct amount of energy and we give more, we see that there is a small amount of heat affected zone around the area which we are machining. But literally, if we give the correct amount of energy, so the heat affected zone will be minimum. I think some of the researchers they have worked with the lasers, and then they have given the figures, and also we have done the machining by using such type of lasers. So where we can see a significant improvement in the quality of the hole which we produce when the duration of the pulse is shorter. So to say that from nanosecond, if you move down to picosecond and then femtosecond, we see that the finishing of the hole is there is a great improvement. And if you take even the ordinary continuous lasers, it will be much worse. So you can see that there is a recast layer around the hole which has been produced, and the recast layer is sticking still, and we can see the quality of the hole is not good. Then when you come to the picosecond laser, so we also see a little decreased, but still we see this kind of recast layer which is formed. But when you use the femtosecond laser, almost it is a perfect hole, but still we have the chance for improving these quality of the hole. So in our work, actually, we machine the holes, and then we have also characterized them. So those details we are going to see further. Now you may ask a question: how do we produce the ultra short pulse lasers? So laser production, I think we are already familiar with, as I mentioned. But then producing these ultra short pulse lasers is really an interesting phenomenon. So in the beginning, like when the technology was developing, so they tried to get the pulse lasers with a mechanical mechanism. They took a disc of metal disc, then cut the slots in it, and then make the laser to pass continuous laser. And then when the disc is rotating, so wherever there is a opening, the laser will go. Other places it is blocked. So that was the crudest way how they were producing the pulse lasers. But after some time, actually, the metal absorbs the laser, and then it gets heated up, and the number of revolutions what we can make is controlled, and literally, practically, we will not be able to use it for much applications. But in the beginning, just to demonstrate the pulse laser, they tried in that kind of a way. But now, what they do is they use the properties of the waves of light. So laser is nothing but light. So they use those properties. And based on that, we have this method. The first method is called mode locking technique. So it is called as a mode locking. So here what happens is that we have the wave, so which is being produced, and then we know that there will be an interference, so where constructive and destructive type of interference depending upon the phase difference, depending on the phase difference. So that is the reason this is also called as phase locked. Okay, so we can actually have a phase difference, and you can tune them in such a way that at few places there'll be a perfect, complete, constructive interference. So when that is happening, so we have I. So the intensity actually squares, I square. So then you get a pulse. And the remaining part actually, there'll be a destructive interference, and there'll be no light. And again, so there'll be a constructive, then the light will come out. So thus, it is actually with the phase difference, we are able to achieve this one, and we can produce these pulses. So then there is a question again. So if you want more energy and also short pulses, what do we do? So in the recent years, so a new technology has come. So actually the persons who are supplying the lasers for us, the amplitude systems and other laser suppliers actually have given this mechanism, and they have told that the chip pulse amplification is one of the technologies where most people are doing and to produce the ultra short pulses. But some of the laser companies actually they will not tell what technology being used inside. But for us, like researchers, we were inquiring, like, please tell us, like, what is the kind of mechanism. So this is the mechanism what they have explained. So it is really an interesting kind of a phenomena. So it's all happening like electro optics, optical mechanism. But I'll tell you how this is happening. So what they do is first they take a short pulse. So it will be giving a short pulse. It is a continuous made into a ordinary short pulse. So like micro or nano kind of a pulse. So then this pulse will be taken, and then the time is stretched. So it is stretched, the pulse is stretched. So that is the reason I said that it is an optoelectronic mechanism. But you can imagine, so if you have a pulse like this, so you stretch it along the timeline. So now we have a long but low power wave, okay, the pulse. Then you take it, and we have like pumps, uh, energy, so which will be inputting the energy into this pulse. So now the height is indicating actually the energy. So then this is the width of the pulse. So now it is a wide pulse. That means the period is more. Like it, if it is a nano pulse laser, we make it like micro pulse laser. Then a laser pumping will be done. So we are going to give higher energy. But this is not what is our aim. So we want a short pulse but higher energy. So then again it will be passed through different optoelectronic mechanism, and then it is compressed. So it is compressed. So thus we have a high pulse energy and short pulse period. So that will be coming out. So this is the way how they are producing. Really, it looks fascinating and interesting. So they use different types of mechanisms. So generally, erbium doped fiber oscillator pump they use for continuous diode laser. Then they make it into a pulse compressor. Then we have what is called as a pulse stretcher. So that is, we are widening it. Then laser pumping is done. Then it is compressed, and finally it's coming out. So here is what we can see: low power short pulse, reduced power stretched pulse. So then amplified power. So we have NDAG laser which will be pumping more energy into this, and then finally it is compressed to required short pulse. Any questions? Okay, are these things which are new or you already familiar with?
Sir, I just have one doubt. So, like
Yeah.
in the femtosecond laser, in the second thing, like CPA, why are they stretching it? Why can't they directly amplify it?
Yeah, actually, pumping the energy. So we need some time actually to pump more energy. So that is the reason we stretch it so that we get enough time we can pump. So then later we actually compress it.
Okay, sir.
Okay, fine. So we'll, yeah, anything else? Any other question? Yeah, we'll continue. So in case you don't understand something, you can stop and ask. Okay. So as yesterday Professor Shreyas Melkut has been telling, so it is not that we just speak what we know, but you can actually stop us and ask us at any time if you have a question. Is it fine? Okay, so this is the interesting mechanism which I have explained yesterday. So when we have an ultra short pulse laser, so we have actually in a material, if you take a conductor, there is what is called as an electron space, free electrons, so which are floating there. And because of that, actually, we have the heat conduction and also the electricity. That is the reason the metals actually are conducting. So this laser matter interaction, I am explaining with reference to metals. So where we have a free electrons and then we have the lattice. I think, hope you'd have heard these terms in your physics. So lattice system, free electrons. And then there'll be what is called as electron phonon coupling. So that will be holding all these things together. Okay. So we have free electrons, we have a lattice, a space lattice, and then we have the electron phonon coupling, which is holding together. If the electron phonon coupling is not enough, actually the free electrons will leave. So then actually the material gets eroded or the material gets removed. So thus in the normal way, when the energy is normal, so these electron phonon coupling will be holding the free electrons. Now what we are doing is when we are giving the laser pulse, so these free electrons first they will be absorbing the energy. So then from low energy level, they'll be going to the higher energy level. So then red color indicates that they are getting heated up. So now once when they get heated up, usually the metals what they do is they want to transfer that energy to the lattice system. So they'll be trying to transfer the energy to the lattice system. Now, as I said, if the pulse width is shorter, even before the energy gets transmitted to the lattice system, so these free electrons which have absorbed the energy will get enough energy to go away or move away from the material. So thus the laser ablation takes place and then these electrons will be gone. So once the electrons are gone, the material is removed. So thus the material removal is happening and there will be no heating of the lattice material. So here we have shown that there are few electrons so which may get this energy also escapes, and that is the reason we have a small amount of heat affected zone. So if they escape, it is fine, but it also heats the surroundings. Actually, theoretically, there are different ways how to explain this phenomena. So, 2 temperature model, and then later actually 3 temperature model and n temperature models have come, and a lot of equations have been given to explain this phenomena. But we have actually worked with 2 temperature model, though it is like proposed initially in 1974, but still it holds good. But the higher modes like 3 temperature model and other one, if you take, you can even get more interesting and close results, but the equations become complicated, and then actually modeling that becomes a challenge. Now, as I said initially, so here we have 2 temperatures here. So what is that is, one is the temperature of the lattice, other one is the temperature of the electrons. So now when you put the laser, so the first, actually the electrons, they will absorb the energy and the temperature increases. And at the same time, small amount of energy is given to the lattice. So the lattice also starts heating up. So then once the pulse is stopped, so they start cooling, and but the electrons which are absorbed starts continue to give the energy to the lattice. So this temperature will be increasing. So once you give the pulse, the electrons will absorb the energy. Then once the pulse is stopped, the temperature will be decreasing. But the lattice, what happens? So these electrons will be transmitting the energy to the lattice and the temperature keeps increasing. But at a particular place, so both these temperatures become equal. And in our case, we have used titanium and its alloys. So that was around 12 picoseconds. So sometimes it can go little higher or it can be even less than that. So thus when we model that, so we find that there'll be a temperature increase and then there'll be a decrease. And continuously when you put the pulses, what happens is, as I said, so the first pulse when you give, the temperature rises and then it starts cooling. Then again you give the second pulse, the temperature goes up and then it starts cooling. So there is an accumulation of already heat. So that is the reason this temperature and this are slightly higher. Yeah, so we find that this and this when you take, so for each pulse, the temperature will be rising. And then we also find that the lattice temperature actually keeps increasing. And that is the reason actually if we put more number of pulses and the energy more than what is required for ablation, so the heat actually gets accumulated. So heat accumulation will be taking place. And similarly, you give 10 pulses or 100 pulses, so we see that temperatures keep increasing. And actually one of my student Kiran Kumar, so he has done his PhD under our guidance, myself and Professor Shanmugam says guidance, who was emeritus professor here, retired from IIT, and he served as an emeritus professor. So we have actually tried to simulate it through the COMSOL software to see how the material removal is actually taking place. And also we tried to characterize. So toward the end of the lecture, I'll show you how, just rather than just getting the depth of the material removed, we have even investigated more to look at how the material removal is exactly taking place. So this also I have said that we can actually have several machining processes, so which we can do by putting those pulses. So it is a simple mechanism. You have a laser pulse, put it on a material, so the material interacts and then it acts in a very interesting way. So now by using that, we can do the machining operations. So we can actually do the drilling. So in drilling also we have different types of drilling. So the first type is, and the general type is called percussion drilling. So wherein we are going to put the pulses continuously just at one place, and then the material will be removed and we get a hole. But now what happens is the diameter of the hole, it depends on the spot diameter. Spot diameter means when you put a laser, so what is the diameter what we get? That is called as laser spot diameter. And also actually there is a phenomena when you take a spot, so the energy actually gets distributed not uniformly but in a Gaussian way. So thus in the center of the pulse you will have more energy, but towards the walls, so it will be tapering down. But still we'll be able to get the diameter of the hole almost close to the pulse width, so the spot diameter. So if this is the spot diameter, so the energy actually gets a distribution, Gaussian distribution like this, so that in the center you have more energy, but then in the peripherals it will be less, but depending on the material and the intensity, so you'll be able to make the holes of this diameter and sometimes slightly more. But then if need bigger diameters, so more than the spot diameter, so we use a method which is called as trepanning. So in trepanning what we do is, if this is the diameter of the hole which we need, so we make the laser pulses to fall along the circumference of the hole. So thus the hole it's actually cutting along the circumference, and then the material will be removed. But now there will be another problem. If I have a thick material, so if you have a thick material, we cannot cut the whole thickness in one stretch. Okay, so we need to remove it layer by layer. So for that, what we do is we use a method called as an helical drilling. So where the diameter of the helix will be equal to the diameter of the hole which we need, and also we actually take it around and then remove the material here. So layer by layer, and then move the laser down. So thus we can produce the holes. So when we produce the holes by percussion drilling, so usually it will be circular, but actually we can also have a beam shaper. So what is called as a beam shaper, by using which we can change the shape. But typically the beam shape will be circular, but if you want different shapes, we can use what is called as a beam shaper, and we can produce different shapes and produce the holes of different shapes, but generally it will be circular. Then in trepanning, we can produce any shape of the hole, because depending on the profile of the hole what you want, we can make the laser to move. So thus we can actually get different shapes. And even in helical drilling, so generally we go as a circular one or elliptical one, or depending on the thickness, we can have different shapes which we'll be able to achieve. So same thing has been explained here in percussion drilling. Usually produce, but in trepanning and other things, we can have different shapes of the holes. And then there is an interesting drilling process which is being used to increase the efficiency of the production of the holes. So we have been talking about, I think even Professor Shreyas Melkote has been telling about the jet engines and then their reliability, all these things we have been talking about. So if you look at this blade, so this is one of the blades which is there in the jet engine. So I also yesterday mentioned that we need cooling holes. So these are the holes actually through which a cold fluid will be circulated, and then the whole film cooling, so will be formed like a layer on the surface of this blade, so that the heat will not move or go to the core of the blade. Otherwise the blade will get even softened, or sometimes even it can get melted. So to avoid that, we have this cooling hole. And here you can see that there are several number of holes. So sometimes it can range even into thousands of holes. Then how do you produce them? If you do it one by one, it takes long time. So as we said, these are pulsed lasers, and usually if you take this as a pulse width, then there will be a gap, then there will be one more pulse which you are going to put, and then there will be a gap, and we are going to put another pulse. So now these are all actually will be in the order of like 10 to the power of minus 9, or 10 to the power of minus 12, or 10 to the power of minus 15. So now what we do with this gap, so we are losing. If you are just producing one hole with one beam, we are wasting a lot of time. This gap, you accumulate it, so much of time we are losing. Instead of doing that, so what they do is they rotate this blade, and then when the first pulse falls, so it will fall on the particular place. So then in the gap, it will be moved to the next one, and then the second pulse will do this, then the third one, fourth. So thus what is happening is we are actually utilizing even the time. So this blisk or the blade will be actually rotating, and the pulses will be put continuously, and we get the drilled holes with a much efficiency. So this is called as a drilling on a fly, because as if you are running around, but still the holes are being produced. So now more details in how we actually carried out these type of holes in our research work. and what are the challenges and why we have been talking about these jet engines every time. So we know that the jet engines perform very well, and their working temperatures are of this order. Okay, so 1600 to 1900 degree centigrade. But then, if you look at the materials, what we call it as the super alloys, so basically titanium, nickel alloys. So these materials actually will get softened beyond these temperatures. Okay, so that means we need, that means the temperature, working temperatures are much higher than the softening temperature of the material. Softening means it may not melt, but actually it starts losing its strength and other properties when you heat above these temperatures. So now to overcome this and to make the jet engine to work at a higher temperatures, there are various mechanisms. So first one, what they do is they coat the turbine blade with what is called as TBC. It is called thermal barrier coating. So a coating will be done so that it will be mostly ceramic kind of a coating. So where the heat will not go to the metal, but this coating will absorb the heat and it will not allow the heat to get transmitted to the blade. That is one. And the second mechanism is through these holes, a cool fluid will be sent and then the film cooling will be taking place, so which removes the heat. So thus, through these mechanisms, so we'll be able to work still at a higher temperatures. And actually, I visited one of the aerospace manufacturing company. So there they have conducted an experiment trying to stop this cooling mechanism and to see what happens. So literally the blade got melted. If you take a tissue paper and then put it in water, how it disintegrates. So similar kind of a phenomena it has happened. So they have recorded that. So thus these cooling mechanisms are very, very important in the engines, jet engines. So this is the setup which I have tried to explain in the previous class, yesterday's class. So now we have developed a mechanism, so where we have the femtosecond laser setup here. So if you would have seen the lasers, uh, earlier years, the setup and the optics which was required were very huge. Even at IIT Madras, uh, we had a laser, so where the whole electronics was like a room kind of a space. But now with a fiber technology, so they have reduced the size. Now probably, I don't know if they have gone backside and visited, so it will be something like a scan, A4 size scanner. So that is the size. So they are able to produce the laser earlier. So to make the fully reflected mirror and partial reflected mirror, and the distance to get more longer, it used to be long and size used to be big. But now with the help of fiber optics, we can produce them with a very, very small size. You can have all this kind of internal reflection and other things. So thus the equipment size has become smaller. Then this laser, you would have seen at the optics, so they'll be brought here, and we have what is called as a galvo scanner. So what is this galvo scanner is that? So it is a reflecting mirror. So where when the laser falls, so it can actually send it to different angles. It can turn. When the mirror turns, so we have the laser falling at different places. So it is called as a galvo scanner. So there are 2D galvo scanners and 3D. So where we can move the laser in different planes, or even height also you can change the focus. But this is actually a 2D galvo scanner. So where if you want to machine a line like this, either we can move the stage from one position to the other position, or we can change the inclination of this galvo scanner and focus. But what will be the challenge will be, so at this angle when it is incidenting, So we have maximum energy, but if this angle of incidence changes, so the energy actually slightly varies. So for a smaller distances, we'd rather prefer to use the galvo scanner. And if you want a quick scan, so it happens in a fraction of a second, so we can use the galvo scanner. Otherwise, we also have these stages here, XYZ stages. So where we can move in X direction or move in Y direction, or we can also actually raise the height in Z direction. So thus we can either use galvo scanner or this movement of the stages in X and Y direction. If you have actually Z scanner, the height actually also, the focusing height also can change. Okay, so this is the mechanism. And then we have the EDM, so where we have a spindle and the tool, which is a wire, which will be put here. And then we have a bath, so where the workpiece will be inserted and then the hole will be done. As I said yesterday, so the laser, femtosecond laser, it's a very good finishing it will give, but the material removal rate is less. So thus we produce the main hole by using the electrical discharge machining, which has a better MRR, and then transfer through this long drive mechanism. So it's a linear stage where we can automatically move it to this stage, and then the laser finishing will be done. So that is the reason it is called as an hybrid micromachining system, by using EDM and the laser. And it is not simultaneous. So even we tried, if we can simultaneously or at one place, we can do EDM and also laser. But that looked to be very complicated because of the way of the mechanisms are entirely different. We need a water bath here and then focusing the laser at this place. So we need a straight line, but we can't get that. So we had a lot of challenges. So we made it as a sequential operation, but automated. So we can make the EDM hole and then transfer it and then finish it by using laser. And here we have actually another important thing is that we have an inline camera. So inline camera means you can see the hole through this camera. Inline means the same axis on which the laser is coming, even the camera also can focus. So thus on the screen we can see what is actually happening. So this is the setup which we have developed. So this is the image of the inline camera. So you can see that laser is falling here, and also the focus of the camera is at this place. So when you are giving the pulses, we can see what is happening. We can't actually see it directly with our eye. It is very harmful. So we need to put the goggles, but even then we should not see it directly, but we can see it on the camera. So sorry, on the monitor through the inline camera. So these are some of the holes which we have produced. So we see that there is a small amount of heat affected zone, but that is because of two reasons. We were still making the optimization to give the number of pulses exactly what is required, and also the exact amount of energy which is required to make a hole. So how do we know how much energy is required? And that is the reason we go for the modeling. So in the modeling, so we need to see what should be the exact amount of energy and how many pulses will be needed. And if you exactly give those number, we get a better holes. But the models, there are a lot of challenges, as I said. So the mathematical equation, the model which we use, there are a lot of approximations because the simulation need to be carried out at 10 to the power of minus. So in a short period, so the computational capacity which is required is huge, and the number of the elements what we take need to be high, because it should be a fine mesh because the material removed in one pulse is just in nanometers. So there's nanometers, femtosecond, so it makes things very complicated. But we have a model, and still that need to be improved. So then, as I said, this laser, when you put on the material, each material behaves differently. So that is something which is interesting. So what we did is one day by mistake actually, so we had a silicon plate and one of my student, so just passed the laser on that. Then a very good, beautiful shapes were formed. So that is actually a phenomena. What is happening is laser-induced periodic surface structures. They call it as lips. So you take a material, just pass the laser on it. So don't give too much energy to melt it, but just pass the laser. So then we see that there'll be a periodic structures, a beautiful structures which will be produced. And you change the energy, you see a different shape. So you change the pulse width, you get a different shapes. So it's a very interesting phenomena. So Shalini is one of the student who did that, and then there is an article actually is there on IITM Tech Talk, so where you see the details of that given there. So also, as Professor Melkut has been explaining yesterday, so we can have the structures which are inspired by the nature, and we can produce different textures on the surfaces, and we can change the property entirely. Okay, so this talk we are going to see in the following lecture, so where we'll be talking about the surface texturing. So if you have observed the lotus leaf, we see that when you put the water droplets, they form into a beautiful spherical balls. So they don't wet the surface. So what is the mechanism? That is because of the nature of the leaf. So we try to produce that kind of a nature by using the texture. So details we'll be seeing in the following classes. So Dr. Niket has completed his PhD. So he has worked on making these kind of structures on a drill bit tool. So by means of which the friction is reduced, and then we are able to see that the cutting forces are also were decreasing. So we'll also look at the details a bit later. So we have actually the collaboration with University of Technology, Sydney, UTS. So where one of my student, Shrikant, is working on this project for producing different types of textures, and then to see how the properties of the surface changes from hydrophobic to hydrophilic. And there are several applications of it which we'll see a bit later. And also these laser applications, we can use them in microfluidic devices. So probably people didn't hear about these microfluidic devices earlier, but during the COVID period, so that COVID test kits which were there, so home kits, so we can buy those kits and we can ourselves test. So those are the examples of these microfluidic devices, and almost every household have used that kind of devices. So we have collaboration with Deakin University in Australia, so where we have been working, Dr. Pawan, Dr. Yugender, and even now Jeshurin and Jennifer are all working in these areas. And we have also actually seen something interesting. So wherein by using these femtosecond lasers, we can produce nanoparticles. So we told about the laser ablation. Yeah, so you put a laser, so it almost like melts, evaporates, and then explodes. Now, if it is in air, usually they go away. But instead, you have a medium, so wherein you can capture them. So even if it is vaporized, if we capture them, So they become like a spherical particles, and we get the size of nanometers. So thus we can actually produce even nanoparticles by using these femtosecond lasers. So we have a collaboration with Hokkaido University in Japan. So where my student who did his MS Murugesh has been completed his PhD work there. So like this, femtosecond lasers have a lot of applications to different areas. So the other application of the lasers is in the 3D printing. So metal 3D printing, so obviously we need a lot of energy, and the machines which are used mostly uses the uh, laser energy to melt either the powder or the wire which is being used. I think we have talked enough, and Professor Shreyas Melkote also has said about the laser shock peening phenomena, so where we can produce the shock waves so that can relieve the residual stresses which are there in the components. I think Professor Shreyas Melkote also has worked on what is called as a laser assisted micro machining. It's called LAM process, so where we can heat the material before the tool makes the contact with the surface, so that the metal gets softened and then we cut it. So that is more efficient rather than cutting the hard material. So thus when you have harder materials, so we can actually heat the material, and then we can use the tool to cut it. Thus we get much better surface finish, and also the cutting forces will be less, and we can increase the tool life. And similarly, laser treatment we can do to get different properties by using the lasers. And another interesting phenomena is also is there, wherein when you change the media, so usually it is air, but instead if you machine a component with under a different media like water, so we found that the finish what we get and the heat affected zone have significantly the heat affected zone has significantly decreased, and the quality of the hole has increased. So we can have even the assistance of the bubbles which are forming for the explosion, for the ablation to take place. So they'll be assisting, and we have a very interesting kind of phenomena which will be happening when we do it under water. Any questions?
So I have a question, sir, and a doubt
Yeah.
in creating holes in the turbine blades.
Mm-hmm.
So while we are creating holes in the turbine blade, the boundary level of the turbine blade will be disturbed earlier.
No, actually, it makes a film over the surface. So, and also we need to remove the heat. So that is the reason we need air or fluid circulation there. So we need the coolant holes
So
to
the
remove
holes
the.
will be visible externally, sir.
Externally means I have shown you a picture, no, where you can see the holes. So the order of the size of the holes is about 200 or 300 micrometers, and sometimes even it can be 500 micrometers.
Okay, sir. So while creating the holes, the characteristics of the blade will be changed or remains constant.
What will change?
Characteristics of the blades while creating
Yeah,
the
yeah.
holes.
Yeah, actually, these blades will be rotating at a very high speed. So, like a turbo machines, no, they are very high speed. And while designing these blades, so we need to consider the holes and then make the balancing. So, mass, weight, and other things need to be balanced. So, with the including the holes, so the analysis will be made. And they have been changing the design of these blades, and nowadays we have different shapes of the holes, and also they are not like 90 degrees, they are inclined, and we have oblique kind of in holes, different shaped holes. They are all not circular, they have different shapes. So we have been working with GTRE in Bangalore, Gas Turbine Research Establishment. So wherein we are trying to see how we can produce the holes and make it more efficient.
Okay, sir, one more question. So,
Yeah.
while creating these holes, while the engine is running, so of course, the dust particles will be also sucked in. Will the holes affect it?
Yeah, so we need to take care. The filtering is always important. So for any engine, so even our IC engines also that can happen. So if when you are taking the air inside inlet, so we have the filters. Maybe in your automobile, when you go for servicing, or even in your two wheelers, you know, the first thing what they will do is they'll check the filter and say, "Sir, we need to change the filter." So you're not changed it for 6 months or 1 year. Have you heard that?
Yes, sir, of course.
Yeah, so obviously they have a filters, so which will not allow the particles bigger than a particular size. So that is also need to be done even for the jet engines.
Okay, sir, thank you, sir.
So now measuring and characterization of these holes is very important. So how do we do that? So now the sizes will be very small. So from 290 micrometers, 200, 300. So this is the range of the holes. So how do we characterize them? And if the depth is higher, it becomes even more difficult for any measuring instrument probe to go inside and to exactly get the shape of it. So we have tried with the different mechanisms. So now here we have what is called as laser scanning confocal microscope. Have you visited the measurements labs? I think it will be done today. Okay, so we'll be looking at the confocal microscope, what we have. So wherein we can capture that image. But in some cases, actually, we had even difficulty to capture by using this laser scanning focal microscope. So we went for AFM, so atomic force microscope. So wherein there'll be a nanometer tip which will be there, and then there are different methods how they measure it. So one is called tapping method, contactor. It comes very close, and then when the probe comes close to the material, there'll be either attractive or repulsive forces, and based on how the stylus is moving, so that will be in few sub micrometers, nanometers, and all. So a small movement will be captured, then it will be magnified by a mirror reflector, and then we can actually reconstruct the shape of the profile of the surface. So this is AFM, so atomic force microscope. So we have used that, and we can see the shape of the hole which has been produced, like when you put one pulse. And also actually we tried to reconstruct the whole shape of the hole, and then with the different instruments when we do, they are almost close, but still they'll be slightly different because in one we use light, in other one we use a probe tape, and then as I said in the previous class, so we have cut the hole and we took a scanning electron microscopy image. So that has given some of the details. So we have put them all together and we tried to reconstruct and see what is the exact profile, what you will get when you put one pulse. So it is called as a single pulse. So we can actually put single pulse or 5 pulses, 10 pulses, or multiple number, and we can study what is going to happen. Also about CT, we have told yesterday. So wherein we can have these samples which can be scanned. I think some of you were asking a question yesterday. So where we can take the component, just keep it there. It is a non-destructive testing. So we don't need to cut, and nothing happens to the sample after the test is carried out. So Thus, it is a NDT test, non-destructive test, and we captured the image. And yesterday, somebody were asking, so how we can reconstruct. So here, I didn't show you the layers, but there'll be n number of like thousands of each plane. They'll have the images, and then the geometric software we can put all these layers together, and then we can get the profile of the hole. So these are cylinders. What you are seeing, they are actually the holes. So you can make the negative of it, or we can even make the whole thing solid, and we can make this thing. All the kind of things we can use by geometric softwares. What we have, they are capable of analyzing the uh, scan data and then reconstruct the whole geometry. Yeah, so this is what we have done. So thanks for your attention. So if you have any questions, we have some time to discuss.
Are there any questions for the participants?
So in 3D printing, by layer only we will print the 3D printing, yes sir?
Yeah.
So in that layer by layer, if I started from one point and while reaching to the second point and starting the second layer, the bonding between the first layer and the second layer will be different only, sir. How will be the bonding characters between layer 1 and layer 2?
Yeah, so actually there are several challenges with 3D printing. So it depends on the size of the print what you make and the profile of the layer. So if it takes longer time, so by the time it comes back to the place where you have printed, so it's gets solidified, and then the adhesion for the next layer decreases, as you said. So we have different mechanisms. So one, what we can do is we can have a heated chamber where you can maintain at a higher temperature. So one of the device what we have 3D printing, so where you'll be visiting, you can see that one. So we have an heated chamber mechanism. And also in some of the mechanisms what we do is we can have one more laser which will be actually heating to a particular temperature before the real 3D printing happens. So you can have a laser which will be going before and then heating that surface, and you can actually 3D print. So like that there are several mechanisms to improve the quality of the print.
Okay, sir.
And it's
Thank
more
you.
challenging for metal printing. Yeah.
Okay, sir.
Good morning, sir.
Yeah.
I have a questions regarding the lasers. So, if supposed to we need to see that vertically or horizontally we can see that apply the laser. If suppose we need to do some customized drillings, so what is the procedures actually? That setup is the default setup, or we can do some customized setup?
Okay, so that is inclined holes, is it?
Yeah, it's inclined, or I just think about that gear teeth cutting. So we see that some housing we are using for teeth cutting. So I'm thinking about that if I use composite fiber and give one square plate, and I need to use the laser to cut the teeth as the specific measurement. So is for this need to do any customized programming or coding or something, anything that I want to know?
Yeah, programming actually, you see now our laser machine also has a software. So by using it's a Kaila is the one, it's a customized software for that particular setup. So where we can give the geometry. So based on the geometry, it's automatically it will be moving. So we can't control, no. So the laser is very fast. So you program it here. So the XYZ coordinates will move according to that, and then they produce the shape. But one challenge here is if it is a 2.5D, 2.5D means it can have any shape, but along the thickness, if there is no variation, it's more easy to produce. But if you have the details on the side walls, then it becomes a challenge. So that one we call it as a 2.5D. That means though it is a 3D component, but on the side walls it is a vertical wall. Now there is no shape or anything on that. So that kind of them we can produce very easily. You can make a 2D drawing of the shape of the gear, then extrude it. So then you get the profile for that particular depth. So you can move the Z direction and then you can cut it. So you have the assistance of the software. So otherwise it becomes very complicated.
Yeah, thank you, sir.
Maybe you can go one more time to our lab and then see that Kaila software which is there associated with that, where you can make the geometry. Or you can make in other softwares and then import it here. And then some refinement will be needed. Then you can give that command so that the laser and the CNC will coordinate. So exactly when it comes to that position, laser starts firing. So and then if there is no cut which is required, the laser will stop, but the stages will move. So then again it will start and then move. So thus different geometries you can produce.
Yeah, thank you, sir.
Yeah, I think it's time now. So we'll close for today. So thank you all for attending. So please maintain time and then your visit to different labs and research park. So please be on time. We thank you all and all our student coordinators who have been helping. Thank you. We'll see you tomorrow. And we'll continue with the Professor Shreyas Melkote's lecture after the tea break. Thank you.
Thank you, sir.